What if I told you that everything we can see, the stars, the planets, even the vast galaxies swirling through space, makes up less than 5% of the universe? The rest, a cosmic enigma hidden in plain sight. The universe we think we know is just the tip of an iceberg, floating in an ocean of invisible forces and mysterious substances we're only beginning to understand. This is the story of dark matter and dark energy, two of the greatest puzzles in modern science and the keys to unlocking the secrets of existence itself. Picture this: you're staring up at the night sky, marveling at the countless points of light. But what if those stars and galaxies were just actors on a stage, performing for an audience that can't see the stagehands, the props, or even the theater itself? That's the reality scientists face when they study the cosmos. Dark matter, an invisible scaffold holding galaxies together, and dark energy, a mysterious force accelerating the expansion of the universe, are the unseen directors of this grand cosmic play. Without them, the universe as we know it wouldn't exist. Yet, despite decades of research, we still don't fully understand what they are. Today, we're diving deep into the shadows of the universe to uncover 25 mind-blowing facts about these elusive phenomena. From ghostly particles that pass through you unnoticed to the startling possibility that dark energy might one day tear reality apart, this journey will challenge everything you thought you knew about space. By the end, you'll see the cosmos in a whole new light, or rather, in the absence of it. So buckle up. We're about to explore the invisible forces that shape everything, and trust me, what you're about to discover will leave you questioning the very fabric of reality. The story of dark matter begins not with a dramatic discovery, but with a nagging inconsistency that refused to go away. Back in 1933, a brilliant but eccentric astronomer named Fritz Zwicky was studying the Coma cluster, a massive group of galaxies over 300 million light-years away. As he measured how fast these galaxies orbited the cluster's center, something didn't add up. The visible stars and gas simply didn't provide enough gravity to keep these galaxies from flying apart. The math was clear: there had to be at least 400 times more mass than what they could see. Zwicky called it Dunkel Materie, dark matter, a term that would haunt astronomy for decades. At first, most scientists dismissed his idea. After all, how could the universe be dominated by something utterly invisible? But the evidence kept piling up. In the 1970s, astronomer Vera Rubin made an even more startling observation while studying the rotation speeds of spiral galaxies. The outer stars were moving just as fast as those near the center, defying the laws of gravity as we knew them. The only explanation, an enormous halo of unseen matter, wrapping around each galaxy like an invisible glove, holding everything together with its gravitational pull. Think of it like a merry-go-round. If you only counted the visible horses, you'd expect the outer ones to move slower. But if unseen weights were hidden beneath the platform, spinning at the same rate, suddenly the motion makes sense. That's precisely what dark matter does on a cosmic scale, an unseen anchor preventing galaxies from tearing themselves apart. Yet here's the twist: despite overwhelming indirect evidence, we still don't know what dark matter actually is. It doesn't emit, absorb, or reflect light. It barely interacts with ordinary matter at all, passing through you right now like a phantom. Zwicky's initial puzzlement has grown into one of science's greatest mysteries. Every time we think we're close to an answer, whether it's hypothetical particles called WIMP or primordial black holes, dark matter slips further from our grasp. But one thing's certain: without this ghostly presence, galaxies would never have formed, stars wouldn't shine, and we wouldn't be here to ponder the mystery at all. Dark matter isn't just hiding in the shadows, it's the master architect of the universe, silently shaping everything we see into a grand, interconnected cosmic web. Imagine the night sky not as scattered stars but as glittering cities strung along invisible highways, with dark matter acting as the unseen scaffolding holding it all together. This vast, intricate structure stretches across billions of light years, a delicate lattice of filaments and voids where galaxies cluster like beads on a string. Here's how it works. After the Big Bang, tiny ripples in the fabric of spacetime left behind uneven patches of density. Dark matter, responding only to gravity, began to clump around these denser regions, pulling ordinary matter, gas, dust, and eventually stars into its gravitational embrace. Over billions of years, these accumulations grew into the sprawling cosmic web we observe today. The galaxies we see are just the luminous highlights tracing the outlines of this hidden framework, like streetlights illuminating the contours of an invisible metropolis. To grasp the scale of this design, picture pouring syrup onto a pancake. As the syrup spreads, it forms thick veins and delicate tendrils with empty spaces in between. That's the universe on the largest scales, a network of dark matter threads weaving through the cosmos, with galaxies congregating at the intersections. Without this hidden architecture, the universe would be a formless soup of matter, never coalescing into the majestic spirals and clusters that fill our telescopes. Even more astonishing, we're part of this web too. The Milky Way sits within a local filament, part of the Laniakea supercluster, an enormous structure hundreds of millions of light years wide, all held together by dark matter's gravitational glue. Every time you look up at the stars, you're glimpsing just one small neighborhood in this sprawling cosmic city, its true blueprint written in the language of the unseen. But what if we've been looking at this cosmic mystery all wrong? Some scientists propose an entirely different solution, one that doesn't require invisible matter at all. Enter modified Newtonian dynamics, or MOND, a bold idea suggesting that our understanding of gravity itself might be incomplete. Instead of invoking dark matter, MOND tweaks the equations of gravity to explain why stars on the edges of galaxies rotate faster than expected. It's like realizing the rules of your board game were slightly off all along, and adjusting them makes the pieces move just right without adding invisible players. At first glance, MOND seems elegant. It successfully predicts the rotation curves of many galaxies without needing dark matter's elusive presence. Think of it as fixing a misaligned wheel rather than inventing an unseen force to explain why the car pulls to one side. Proponents argue nature often favors simplicity, so why introduce mysterious, undetectable particles when a small adjustment to gravity could solve the puzzle? But here's where things get complicated. While MOND works beautifully for individual galaxies, it stumbles when faced with the larger cosmic picture. Take galaxy clusters, for example. These massive structures where hundreds of galaxies orbit a common center require far more gravitational pull than MOND can provide. Observations of colliding clusters like the famous Bullet cluster reveal something startling. The visible matter gets stuck in the crash, while the bulk of the mass, deduced from gravitational lensing, sails right through. It's as if two crowds of people clashed, but the real weight was carried by ghosts walking untouched between them. MOND struggles to explain this unless, ironically, it reintroduces some form of invisible matter, undermining its own premise. Then there's the cosmic microwave background, the afterglow of the Big Bang. Its intricate patterns match simulations that include dark matter with astonishing precision, while MOND-based models falter. It's like trying to reconstruct a symphony with half the instruments missing. The harmony just isn't there. Even more damning, the way dark matter's gravitational scaffolding guided the formation of galaxies aligns seamlessly with what we observe, while MOND offers no comparable mechanism for how the universe grew into its current structure. That's why most scientists still bet on dark matter. It's not just about one anomaly, it's about a web of evidence spanning the entire universe, from the tiniest dwarf galaxies to the largest superclusters. MOND, for all its ingenuity, feels like patching a single hole in a sinking ship, while dark matter theory builds a sturdier vessel from the keel up. Yet the debate isn't over. Science thrives on challenges to the status quo, and MOND keeps researchers honest, pushing them to test every assumption. After all, the universe owes us no guarantees, only clues. And whether the answer lies in invisible particles or rewritten laws of physics, one thing's certain: the truth will be far stranger than we've dared to imagine. The most compelling snapshot of dark matter's existence doesn't come from equations or simulations. It's etched across the cosmos in the wreckage of two galaxy clusters that collided at a staggering speed of millions of miles per hour. Known as the Bullet Cluster, this cosmic crash site reveals something extraordinary. The visible matter and the gravity holding the clusters apart didn't behave the same way. Imagine two crowds of people running into each other. Their bodies collide and slow down, but their shadows keep moving forward unaffected. That's essentially what happened here, with one critical difference: the shadows carried most of the mass. When astronomers aimed telescopes at this cosmic collision, they mapped it in two ways. First, X-ray observations showed where the ordinary matter, superheated gases, had piled up in the center like cars crumpled in a highway pileup. But when they measured the cluster's total mass using gravitational lensing, the way their gravity bends light from background galaxies, the real surprise emerged. The bulk of the mass wasn't where the gas was. It had sailed ahead in two distinct blobs, barely interacting with the visible wreckage. The only explanation: an invisible form of dark matter had passed through the collision like a ghost, its gravity warping space-time exactly where no visible material existed. This wasn't just a hint, it was a smoking gun. Ordinary matter interacts electromagnetically, so when clusters collide, gas particles smash together and slow down. But dark matter barely notices. It doesn't interact with light or other matter except through gravity, so it coasts straight through, dragging its enormous gravitational footprint with it. The Bullet Cluster became the first observable proof that most of the universe's mass isn't just hidden, it's fundamentally different from anything we're made of. Critics of dark matter theory had to confront an irrefutable truth. No tweak to gravity could explain why the mass and visible matter divorced so cleanly in this collision. It's like watching a magician's trick where the audience expects sleight of hand only to realize the magician never touched the coin at all. The coin simply obeyed different rules. That's the unsettling beauty of the Bullet Cluster. It doesn't just suggest dark matter exists. It shows us exactly where it isn't, and in doing so, reveals where it must be. Yet the story gets even stranger. Similar collisions like the Musket Ball Cluster and Able 528 have since reinforced this pattern. Each time, the dark matter's behavior defies expectations, proving it's not a fluke but a fundamental feature of the cosmos. These cosmic crash sites are like nature's own particle detectors, offering glimpses into the invisible architecture that holds the universe together, one gravitational shadow at a time. If dark matter were a criminal, scientists would have quite the lineup of suspects, each with motives that fit parts of the cosmic crime scene, but lack the smoking gun of direct evidence. At the top of the list, WIMP, or weakly interacting massive particles. These hypothetical heavyweights are a favorite among physicists because they'd neatly solve multiple puzzles at once. Picture them as elusive ninjas, massive enough to exert gravitational pull, but so stealthy they rarely bump into ordinary matter. Billions might be streaming through you right now, leaving no trace. Underground labs like Italy's Gran Sasso or South Dakota's Sanford Lab have spent decades hunting for WIMP using ultra-sensitive detectors shielded from cosmic noise, waiting for that 1 in a trillion chance a particle collides with an atom. Yet despite heroic efforts, the detectors remain silent, leaving scientists to wonder, are WIMP just too shy, or are we chasing a ghost? Then there are axions, the featherweights of the dark matter world. Theorized in the 1970s to solve a quantum puzzle, these ultra-light particles could collectively outweigh everything visible in the universe. Imagine trillions of fireflies, each weighing almost nothing, but together forming an invisible fog that bends light and tugs on galaxies. Experiments like ADMCS in Washington state use powerful magnets to coax axions into revealing themselves by converting into microwaves. But like tuning a radio to a station that might not exist, researchers keep scanning frequencies with no confirmed signal. The irony: if axions are real, their sheer abundance means they're everywhere, yet they've mastered the art of hiding in plain sight. Perhaps the most dramatic candidates are primordial black holes, cosmic relics from the universe's first chaotic seconds. These wouldn't be the black holes formed by collapsing stars, but microscopic ones smaller than an atom yet as massive as a mountain. Think of them as cosmic landmines littering space and warping their surroundings with invisible gravity. Some theories suggest they could explain dark matter's grip on galaxies, but here's the catch. We've seen no evidence of their gravitational lensing effects or the explosions they'd produce when evaporating. Even more puzzling, if they dominated dark matter, why haven't we detected the ripples they'd create in the delicate fabric of space-time? The frustration is palpable. Each candidate fits pieces of the puzzle. WIMP explain large-scale structure. Axions avoid conflicting with particle physics. Primordial black holes require no new particles, yet none have stepped into the spotlight. It's like having three keys that almost fit a lock but won't turn. Some researchers even speculate dark matter could be a mix of these or something entirely stranger, like supersymmetric particles or exotic quantum fields. What's clear is this: the longer the hunt drags on, the more we're forced to question our assumptions. Maybe dark matter isn't one thing but many, a cosmic cocktail of mysteries we've only begun to uncork. One thing unites all these searches: the humbling realization that most of the universe refuses to play by the rules we've written. Every null result, every quiet detector, is a reminder that nature owes us no answers, just clues scattered like breadcrumbs in the dark. And until one of these candidates steps forward, the greatest enigma in physics remains tantalizingly out of reach. The Milky Way isn't just a glittering spiral of stars, it's a cosmic island drowning in an invisible sea. Surrounding our galaxy like a phantom embrace stretches an enormous halo of dark matter, 10 times wider than the visible disk we see in telescope images. Picture this: if the Milky Way were a city, its glowing downtown would be where most stars reside, but the real metropolis extends far into the suburbs, defined by unseen streets and structures we can only map through their gravitational whispers. This hidden architecture shapes everything. Stars on the outer edges of our galaxy don't move as they should based on the visible matter alone. Instead, they race along at speeds that would fling them into intergalactic space, if not for the immense gravitational grip of the dark halo. It's like watching cars zip around a roundabout at the same speed, whether they're near the center or the edge. The only explanation: an unseen hand, dark matter, keeping them in check. Astronomers measure this influence through the motions of distant stars and satellite galaxies, like the Large Magellanic Cloud, which orbits the Milky Way at nearly 400,000 miles per hour. Without the dark halo's extra mass, these celestial hitchhikers would have escaped long ago. Even more telling, the halo's gravity bends the paths of speeding stars called hypervelocity stars, cosmic runaways ejected from the galactic center, curving their trajectories like invisible speed bumps. But here's what's truly mind-blowing: this halo isn't a smooth, uniform cloud. Simulations suggest it's lumpy, filled with dense clumps and tendrils left over from the Milky Way's violent past. Some of these dark matter subhalos might host their own captive stars, creating ghostly satellite galaxies we can barely detect. Others could be pure dark matter, drifting like silent icebergs through our galactic neighborhood. The Milky Way's halo is more than just evidence for dark matter, it's a fossil record of our galaxy's growth. Over billions of years, it's devoured smaller galaxies, each merger leaving behind dark matter scars. If we could see it, the halo would resemble a tree's rings with layers marking every cosmic collision. Yet for all its grandeur, this invisible structure remains frustratingly elusive. We feel its pull, map its contours, but still can't say what it's made of, a reminder that even our home galaxy keeps its deepest secrets hidden in the dark. Without dark matter's gravitational scaffolding, the universe might have remained a lifeless void, a thin soup of hydrogen and helium drifting endlessly apart. Here's why. In those critical moments after the Big Bang, ordinary matter was too hot and energetic to clump together on its own. Atoms zipped around at breakneck speeds, resisting the gentle tug of gravity. But dark matter, unaffected by the heat and radiation, began gathering first, creating gravitational wells deep enough to trap ordinary matter like cosmic potholes. Over billions of years, these pockets grew denser, collapsing into galaxies where stars could ignite, forging the heavier elements carbon, oxygen, iron, that make up everything from planets to people. Think of it like a campfire in a windy field. Without a ring of rocks to shield the flames, the sparks would scatter and die. Dark matter provided that protective barrier, corralling gas and dust into stellar nurseries where nuclear fusion could work its alchemy. No dark matter, no stars, no supernova to blast heavy elements into space. We'd be left with a universe of primordial gas, forever too thin to spark the chemistry of life. Even Earth's gold, the iron in your blood, the calcium in your bones, all were forged in stellar furnaces made possible by dark matter's unseen hand. The numbers are staggering. Simulations show that without dark matter's extra gravity, galaxies would have formed hundreds of times slower. Their stars spread so thinly that collisions, the violent crashes needed to create heavy elements, would have been vanishingly rare. It's the difference between a bustling city and a handful of isolated villages. In a dark matter-free universe, the cosmic city lights might never have switched on. But here's the twist. Dark matter's role wasn't just about density, it was about timing. Those first galaxies had to form early enough for generations of stars to live, die, and seed the cosmos with life's ingredients before expansion diluted everything. Dark matter's relentless pull accelerated that timeline, giving the universe a head start. Without it, we might still be waiting for the first planets to form, let alone life. So the next time you gaze at the night sky, remember, the very atoms that let you wonder about the cosmos owe their existence to shadows we can't even see. Deep beneath Italy's Gran Sasso Mountain, shielded from cosmic rays by nearly a mile of rock, a peculiar signal has been flickering for over 2 decades, one that just might be our first whisper from the dark matter universe. The DAMA/LIBRA experiment, a vat of ultra-pure sodium iodide crystals, has detected a rhythmic pulse in its data, a spike in particle interactions every June, fading every December like clockwork. The team behind it claims this could be Earth plowing through a galactic river of dark matter particles as we orbit the Sun, creating an annual modulation only detectable with extreme precision. Imagine walking through a snowstorm. If you moved faster, you'd feel more flakes hitting your face. Similarly, as Earth's motion adds to the Sun's journey through the galaxy each summer, we might encounter more dark matter flakes, producing DAMA tantalizing signal. But here's where the controversy ignites. No other experiment has replicated this result. Not the LUX detector in South Dakota, nor Xenon 1 ton under the same Italian mountain, nor Korea's Cosine 100. These rivals used different materials, liquid xenon instead of sodium iodide, and have found nothing. Critics argue DAMA might be detecting subtle seasonal changes in background radiation or even quirks in their own equipment. It's like 2 chefs tasting the same soup. One insists it's spicy while the other swears it's bland. The scientific community is split, with some calling it a statistical fluke and others wondering if dark matter interacts in ways we didn't anticipate, perhaps coupling with ordinary matter through unexpected channels. The stakes couldn't be higher. If DAMA is right, we've been staring at dark matter's fingerprint for years without recognizing it. If wrong, it's a cautionary tale about how easily patterns can fool us. Yet this debate isn't failure, it's science in action. Every challenge to DAMA claims forces researchers to sharpen their methods, double-check assumptions, and design even more sensitive detectors. Future experiments like SABRE, with identical setups in both hemispheres to rule out local effects, may finally settle the score. Until then, DAMA enigmatic signal remains a beacon, or maybe a mirage, in the quest to unmask the universe's darkest secret. For centuries, scientists assumed the universe's expansion was slowing down, a cosmic sigh after the explosive energy of the Big Bang. Gravity, after all, pulls things together. Throw a ball in the air and it eventually falls back. Apply that logic to the cosmos, and every galaxy should be gradually decelerating, drawn inward by the collective tug of all that mass. But in 1998, two teams of astronomers made a discovery so shocking it overturned everything. Studying distant supernova, the brilliant explosions of dying stars, they found the universe wasn't just expanding, it was accelerating, as if some invisible force had stomped on the cosmic gas pedal. The key to this revelation lay in Type 1, a supernova, celestial flashbulbs so consistent in brightness they're called standard candles. By measuring how dim these explosions appeared compared to how bright they should be, scientists could calculate their distance. But there was a twist. The supernovae were fainter than expected, meaning they were farther away than their redshift suggested. The universe hadn't just expanded, it had sped up along the way. Imagine marking two dots on a deflating balloon, then watching in disbelief as the balloon not only reinflates but does so faster and faster, stretching those dots apart at an ever-increasing rate. That's exactly what the data revealed. The implications were staggering. For decades, cosmologists had debated whether the universe would end in a big crunch, collapsing back on itself, or a big freeze, expanding into eternal cold. Suddenly, neither scenario fit. Instead, the universe seemed filled with an unknown force combating gravity, dark energy. The leading theory, Einstein's long-discarded cosmological constant, a term he'd once added to his equations to keep the universe static, then called his greatest blunder when expansion was discovered. Now it was back in vogue as the simplest explanation. Empty space itself might possess an intrinsic energy, pushing galaxies apart faster the more space stretches between them. Yet the mystery only deepens. Dark energy appears to make up roughly 68% of the universe's total energy content, far more than dark matter or visible matter combined. Its effects only became dominant about 5 billion years ago, when the universe's expansion had stretched matter thin enough for dark energy's repulsive push to overpower gravity's pull. Before that, the cosmos was smaller and denser, with gravity firmly in control. Now, dark energy reigns, driving galaxies apart so aggressively that in trillions of years, distant star systems may vanish beyond an unreachable horizon, leaving future civilizations with a sky nearly empty of galaxies. What's truly unsettling is that we have no idea what dark energy actually is. Is it vacuum energy, a new fundamental field, or something even stranger, like a flaw in our understanding of gravity itself? The discovery that upended cosmology left us with more questions than answers, proof that the universe, even in its grand old age, still has the power to surprise us. Einstein called it his greatest blunder, an idea so embarrassing he struck it from his equations and dismissed it as a youthful folly. Yet decades after his death, this abandoned brainchild would return to haunt cosmology, revealing itself as the key to understanding dark energy. It all started in 1917, when Einstein applied his theory of general relativity to the entire universe. His equations kept predicting a cosmos that was either expanding or collapsing, but astronomers at the time insisted the universe was static, eternal, and unchanging. So Einstein introduced a fudge factor, the cosmological constant, represented by the Greek letter lambda lambda. This mathematical term counterbalanced gravity's pull with an invisible repulsive force, creating the illusion of stability in his calculations. Then came Edwin Hubble's bombshell discovery in 1929. The universe wasn't static at all. Galaxies were racing apart, proof of cosmic expansion. Einstein, horrified he'd missed this possibility, banished the cosmological constant from his work, calling it superfluous and theoretically unsatisfactory. It became a cautionary tale about overcomplicating theories to fit flawed assumptions. But history had other plans. Nearly 70 years later, when astronomers found the universe's expansion was accelerating, they realized Einstein's discarded constant wasn't a mistake, it was prophetic. That same repulsive force he'd imagined to keep the universe static actually described how dark energy was pushing galaxies apart faster and faster. The irony is delicious. Einstein's blunder turned out to be one of the most profound insights in physics. He just didn't live long enough to see it vindicated. Today, lambda is central to our best model of the cosmos, the lambda-CDM model. It suggests dark energy behaves exactly like Einstein's constant, an unchanging energy woven into the vacuum of space itself. The more space expands, the more this energy grows, creating a runaway effect where galaxies are forever tugged apart by the fabric between them. What's remarkable is how close Einstein came to predicting dark energy while dismissing its reality. His intuition told him empty space couldn't be truly empty, it had to have some intrinsic properties. Modern quantum physics agrees, suggesting virtual particles constantly flicker in and out of existence in the vacuum. But here's the kicker. When we calculate how much energy this quantum activity should contribute to the cosmological constant, the result is a number 120 orders of magnitude too large enough to rip atoms apart instantly. This staggering mismatch, known as the vacuum catastrophe, means we're still missing something fundamental. Einstein's story is a humbling reminder that even geniuses misunderstand their own breakthroughs sometimes. He saw lambda as a mathematical crutch, but the universe knew better. Now, as astronomers measure dark energy's effects with increasing precision, we're left to wonder, how many of today's mistakes will tomorrow reveal as hidden truths? Picture the universe as a runaway train hurtling faster and faster into the void, not because it's being pulled, but because the tracks themselves are stretching beneath it. That's the eerie reality of dark energy, a force so relentless that it doesn't just push galaxies apart, it ensures the space between them grows exponentially. And here's the terrifying twist: the more space expands, the stronger dark energy's grip becomes. Unlike gravity, which weakens with distance, dark energy operates on a cosmic feedback loop, growing more dominant as the universe stretches thinner. This isn't just theoretical doom-scrolling. Scientists have calculated a possible fate called the Big Rip, where dark energy's acceleration crosses a critical threshold. First, galaxies would fly apart, their stars untethered like beads from a snapped string. Next, solar systems would unravel, planets ripped from their orbits. Then, stars and planets themselves would disintegrate as the force overcomes gravity's hold. In the final, shuddering moments, even atoms would be torn apart, protons and electrons shredded by the same exponential expansion that once pushed galaxies apart. The universe wouldn't end with a collapse or a freeze, but with a violent, fundamental dissolution of spacetime itself. The timing, trillions of years from now, long after the last stars have burned out. But the mechanics are already at work. Dark energy's density appears constant, meaning every new cubic meter of space created adds more repulsive force to the cosmic ledger. It's like filling a balloon with air that never loses pressure eventually. The rubber stretches too thin and pops. In this case, the rubber is the very fabric of reality. What makes the Big Rip so unsettling isn't just the scale of destruction, it's the inevitability. If current observations hold, no force in the universe can stop it. Not black holes, not dark matter, not even the nuclear bonds holding matter together. dark energy doesn't play by the rules we know, it rewrites them. Some theories even suggest that before the rip, we'd reach a point where light from distant galaxies can no longer reach us, leaving civilizations of the future trapped in isolated pockets of darkness, unaware of the larger universe slipping away. Yet there's a strange beauty in this cosmic doomsday. The same force that might one day tear reality apart also gave rise to everything we know. Without dark energy's subtle push, galaxies might have clustered too densely, colliding and merging until the universe became a chaotic jumble. Instead, it's the delicate balance between dark energy's repulsion and dark matter's pull that crafted the structured, life-friendly cosmos we call home. The very force that could destroy everything may also be the reason we're here to ponder it, a paradox as haunting as the dark energy itself. What if dark energy isn't a constant force at all, but something far stranger, a cosmic chameleon that grows stronger or weaker over time? This is the radical proposition of quintessence, a theory that challenges Einstein's static cosmological constant with a dark energy that evolves. Imagine the universe as a symphony where gravity plays the bass line. Dark matter provides the rhythm, and dark energy, instead of being a steady, unchanging note, swells and fades like an unpredictable soloist. That's quintessence in a nutshell, dynamic, mutable, and utterly different from the Lambda model's portrayal of dark energy as a fixed property of space. The name comes from Aristotle's fifth element, the celestial substance beyond earth, air, fire, and water. In modern cosmology, it represents a hypothetical field permeating space, one that could either repel or attract depending on its configuration. Unlike the cosmological constant's immutable push, quintessence might have started weak after the Big Bang, allowing gravity to dominate and galaxies to form, then strengthened over billions of years to drive today's accelerated expansion. Some versions even suggest it could flip signs in the distant future, turning from repulsive to attractive and collapsing the universe in a big crunch. This isn't just philosophical speculation. Observations of distant supernova and baryon acoustic oscillations, the faint ripples frozen in the distribution of galaxies, hint that dark energy's strength might not be perfectly constant. The data is subtle, like detecting a singer's vibrato in a recording full of static, but it's enough to keep quintessence theorists awake at night. Their models introduce equations where dark energy's density changes as the universe expands, like a spring losing tension or a battery draining. The implications are profound. If true, the fate of the cosmos hinges less on a fixed constant and more on a rolling cosmic landscape we've barely begun to map. Critics counter that quintessence adds unnecessary complexity. Lambdactum, with its single, elegant constant, explains nearly every observation with staggering precision. Introducing a dynamic field feels like swapping a well-tuned metronome for a drummer who might speed up or slow down on a whim. But proponents argue nature rarely adheres to human preferences for simplicity. After all, we once thought the sun revolved around a stationary Earth. How arrogant to assume dark energy must conform to our neatest equations. The debate crystallizes around a phenomenon called the equation of state, denoted by W. In lambdactum, W is exactly -1, meaning dark energy's repulsive force never varies. Quintessence allows W to fluctuate, potentially dipping below -1 phantom energy or rising towards 0 decaying dark energy. Current measurements pin W close to -1, but the error bars leave room for surprises. Future telescopes like ESA's Euclid and NASA, a Roman space telescope, aim to shrink those uncertainties, hunting for tiny deviations that could signal quintessence at work. Here's where it gets eerie. If W is indeed less than -1 phantom territory, the universe could face a fate even more extreme than the Big Rip. Phantom energy would grow infinitely stronger as space expands, tearing apart spacetime's fabric not in trillions of years but potentially within a finite window. It's the difference between a slow-acting poison and a detonating bomb. Yet quintessence could just as easily soften dark energy's impact, offering a gentler future where expansion gradually plateaus. The truth might lie between these extremes or in some hybrid model we've yet to conceive. What makes quintessence so compelling isn't just its scientific novelty, it's the philosophical shift it represents. A dynamic dark energy implies the universe isn't governed by fixed rules but by evolving processes, a cosmos more alive than we ever imagined. Whether it's real or not, the theory reminds us that even our most confident assumptions about reality might be due for revision. After all, if the past century of cosmology has taught us anything, it's that the universe loves to subvert expectations. The universe's ultimate fate hinges on a single question: will dark energy keep bullying gravity forever, or is this cosmic tug of war destined for a sudden, violent upset? Astronomers have narrowed it down to 3 possible endings, each more mind-bending than the last. The frontrunner, endless expansion, a slow, cold fade into darkness. Picture a campfire dwindling to embers, but instead of flames, its entire galaxies receding until neighbors vanish beyond an unreachable horizon. In this scenario, dark energy's relentless push keeps accelerating, stretching space so thin that star formation eventually stops, black holes evaporate, and the universe becomes a desolate wasteland of isolated particles. Distant civilizations would watch their skies go black as light from other galaxies red shifts into oblivion, leaving them alone in an ever-expanding void. It's the most likely outcome based on current data, but likely doesn't mean certain. Then there's the poetic alternative, the Big Crunch. Imagine dark energy isn't constant but weakens over time, allowing gravity to finally win the cosmic arm wrestle. Galaxies would reverse course, rushing back together in a mirror image of the Big Bang. Space itself would shrink, temperatures skyrocketing until atoms, nuclei, and even space-time tear apart in a fiery collapse. It's the universe hitting the rewind button, but here's the twist. For this to happen, dark energy would need to transform into something akin to its opposite, a notion that clashes with everything we've observed so far. The only way a big crunch occurs is if quintessence, that dynamic dark energy we touched on earlier, flips from repulsive to attractive, essentially turning the universe into a runaway elevator that suddenly plummets. Current measurements give it slim odds, but in cosmology, unlikely isn't the same as impossible. Now, brace for the most unsettling scenario: vacuum decay. This isn't just the end of the universe, it's a rewrite of reality's rulebook. Quantum physics suggests our universe might exist in a false vacuum state, like a marble resting precariously on a hillside. If some cosmic nudge sends it rolling downhill, a bubble of true vacuum could form where the fundamental constants, gravity, electromagnetism, even the speed of light, have different values. This bubble would expand at the speed of light, erasing everything in its path without warning. One moment, stars shine and planets orbit. The next, atoms lose their ability to bond, matter disintegrates, and the laws of physics as we know them cease to exist. The terrifying part, it could already be happening somewhere beyond our cosmic horizon. We wouldn't see it coming until it was too late. Here's the paradox: while vacuum decay is theoretically possible, it's also the least probable. The universe has existed for 13.8 billion years without collapsing into a new vacuum state, suggesting our hillside is steeper than we fear. But like a fire drill for reality, the mere possibility forces us to confront how delicately balanced existence might be. Whether it's the long goodbye of endless expansion, the dramatic reversal of a big crunch, or the quantum apocalypse of vacuum decay, one thing's clear: dark energy holds the keys to the cosmos's finale. And the closer we look, the more we realize how much we still don't know about the force shaping our ultimate destiny. Here's something that keeps cosmologists up at night, a puzzle so strange it's called the cosmic coincidence problem. Picture two runners in a marathon, one sprinting ahead while the other slows to a crawl. By sheer chance, they end up side by side just as you glance at the race. That's essentially what's happening with dark energy and matter. For most of the universe's history, matter's gravitational pull dominated, slowing expansion. Dark energy existed, but its repulsive effect was negligible, like a whisper drowned out by a shout. Then, around 5 billion years ago, something flipped. As the universe grew larger and matter spread thinner, dark energy's push suddenly became the dominant force. Now here's the eerie part. Today, the density of dark energy and the density of matter are almost exactly the same. Not a factor of 10 apart or 1,000 nearly identical. Statistically, this shouldn't happen. Matter dilutes as space expands. Dark energy's density stays constant or possibly increases. Their ratio should have been wildly different at almost any other point in cosmic history. It's like tuning into a radio station at the exact millisecond your favorite song starts, possible, but astronomically unlikely. Why does this unsettle scientists? Because it feels suspiciously fine-tuned. If dark energy had been slightly stronger earlier, galaxies would never have formed. Space would have expanded too quickly for gravity to pull matter together. Slightly weaker, and the universe might have collapsed in a big crunch before life could arise. Instead, we exist in this razor-thin sliver of time where the two forces briefly balance, allowing us to observe them both. Some theorists argue this isn't coincidence at all. Their anthropic principle suggests that in a multiverse where countless universes have different physical constants, only those with conditions like ours would harbor observers to ponder the mystery. Others propose dynamic dark energy models like quintessence, where the balance isn't accidental but the result of unseen physics. Then there's the radical idea that we're misreading the data entirely, that dark energy's apparent dominance is an illusion caused by our position in a vast cosmic void. But the simplest explanation, we might just be incredibly, improbably lucky. The universe doesn't owe us an explanation for its timing, yet this fleeting equilibrium, this cosmic snapshot where two fundamentally opposed forces briefly hold each other in check, reminds us how fragile and fleeting our understanding of reality truly is. The Hubble tension isn't just a scientific disagreement, it's a full-blown cosmic mystery threatening to upend our understanding of dark energy. Here's the problem. Two of the most reliable methods for measuring how fast the universe is expanding keep giving us different answers, and no amount of double-checking can make them agree. One approach uses the cosmic microwave background, the afterglow of the Big Bang, to calculate the Hubble constant from the early universe's conditions. The other relies on tracking pulsating stars and exploding supernova in nearby galaxies to measure today's expansion rate. Both methods are meticulous, both involve Nobel Prize-winning physics, yet they stubbornly refuse to align. It's like having two clocks built by master watchmakers, each insisting it's a different time with no way to tell which one's wrong. The numbers tell the story. Measurements from the Planck satellite studying the cosmic microwave background peg the universe's expansion at around 67 kilometers per second per megaparsec. But observations of Cepheid variable stars and Type 1a supernova, our cosmic yardsticks, consistently land near 73. That 6-kilometer gap might seem small, but in cosmology it's a chasm. Statistically, the odds of this being a fluke are less than 1 in a million. Either we're missing something fundamental about how the universe works, or dark energy isn't behaving the way we thought it would. One tantalizing possibility, dark energy isn't constant but evolving, growing stronger over time. This would mean Einstein's cosmological constant, the bedrock of our current models, needs revising. Imagine driving a car where the gas pedal gradually sinks farther the longer you hold it down. That's what dynamic dark energy could be doing to cosmic expansion, not just maintaining pressure but increasing it, throwing off our measurements. Alternatively, there might be unseen particles or forces at play, an exotic form of dark matter, perhaps, or even gravity itself working differently on large scales than we've assumed. Then there's the wild card. What if the early universe was cooler or more matter-dense than we've calculated? Tiny variations in those initial conditions could ripple forward, distorting our measurements like funhouse mirrors. Some theorists propose a brief, early phase of dark radiation that tweaked the cosmos's starting parameters. Others suggest we're seeing evidence of parallel universes tugging on ours through higher dimensions, though that remains firmly in speculative territory. The most unsettling implication: our models of dark energy might be incomplete because the universe itself is more complex than we've dared to imagine. For decades, we've assumed a smooth, uniform cosmos where dark energy's effects are predictable. But if the fabric of spacetime has hidden wrinkles or uneven densities, like a stretchy blanket with some patches stiffer than others, it could explain why local and distant measurements disagree. We might be like ants on a trampoline, trying to deduce its shape from a single point while unseen dips and rises warp our perspective. Every new observation deepens the puzzle. The James Webb Space Telescope's infrared eyes recently confirmed the discrepancy isn't due to faulty data, while gravitational wave detectors offer a third, independent method that seems to side with the faster expansion camp. This isn't just academic nitpicking, it's a potential revolution in cosmology. If the Hubble tension holds, we could be on the verge of discovering a new cosmic ingredient or rewriting the rules of gravity itself. Either way, the universe is sending us a clear message. There's more to this story than we've been told. Computer simulations tell us that the Milky Way should be swarming with hundreds of tiny satellite galaxies, clumps of stars held together by their own dark matter halos, orbiting our galaxy like moths around a porch light. But when astronomers actually count them, they find far fewer than expected. This glaring mismatch, known as the missing satellites problem, has haunted astrophysicists for decades. It's as if someone erased half the actors from a play's cast list, leaving us to wonder, where did the rest of the cosmic supporting characters go? The roots of this puzzle trace back to the way dark matter behaves in supercomputer models. These simulations show that after the Big Bang, dark matter should have clumped into countless small halos, gravitational potholes where gas could collect and form stars. Given the Milky Way size, we'd expect at least several hundred of these dwarf galaxies to survive to the present day, yet only about 50 have been spotted. Some are so faint they were only discovered in the past decade, hiding in plain sight like cosmic ghosts. The rest nowhere to be found. One possible explanation is brutally simple. Maybe most of these dark matter clumps never lit up with stars at all. Picture a construction site with hundreds of half-built houses. The frameworks are there, but without walls or roofs, they're invisible from a distance. Similarly, the smallest halos might have lacked enough gas to ignite star formation, leaving them as dark galaxies devoid of the glowing beacons we rely on for detection. The most massive dwarfs, like the Large Magellanic Cloud, shine brightly because they retained enough gas, while their smaller cousins faded into obscurity. But here's where it gets even stranger. Even accounting for these invisible halos, the number of observed dwarf galaxies is still too low, and their distribution is all wrong. Simulations predict they should orbit randomly, yet real dwarf galaxies appear oddly synchronized, clustering in a thin plane around the Milky Way like flies stuck to a window pane. This suggests something fundamental might be missing from our models. Perhaps dark matter interacts with itself in ways we haven't accounted for, creating friction that erases the smallest halos over time. Or maybe our understanding of how stars form in tiny galaxies is flawed, with supernova or black holes blowing away the gas before more stars can ignite. The implications are profound. If the missing satellites problem stems from gaps in our dark matter theory, it could mean the particles we've been hunting behave differently than predicted. Maybe they're warmer or more interactive than the standard cold dark matter model assumes. Alternatively, the solution might lie in the messy physics of star formation itself. Young galaxies in the early universe faced a hostile environment. Intense ultraviolet radiation from the first stars could have stripped gas from fledgling dwarfs, leaving them stillborn. Some astronomers are turning to controversial ideas like fuzzy dark matter, a hypothetical ultralight particle that would blur the smallest halos out of existence, or even alternate gravity theories that eliminate dark matter entirely. But every proposed fix comes with trade-offs, often breaking other well-tested aspects of cosmology. It's like trying to solve a Rubik's Cube where every twist that aligns one color scrambles another. What makes this mystery so captivating isn't just the missing dwarfs themselves, it's what they represent. These tiny galaxies are the fossils of the universe's formative years, and their absence hints at forces or particles we've yet to imagine. Each new discovery, like the ultra-faint dwarf Segue 2, a galaxy so dim it was mistaken for a star cluster for years, adds another piece to the puzzle. The truth may lie in the darkness, waiting for the next generation of telescopes to finally bring it into the light. To understand the universe's recipe, we need to look back to its infancy, a time when light itself was trapped in a dense, glowing fog. The cosmic microwave background, or CMB, is that baby picture, the oldest light we can see, emitted just 380,000 years after the Big Bang. When the Planck satellite mapped this faint glow with unprecedented precision, it didn't just capture wrinkles in space-time, it revealed the exact ingredients of the cosmos. The numbers are staggering. Ordinary matter, the stuff of stars, planets, and us, makes up a mere 4.9%, dark matter 26.8%, and dark energy a dominant 68.3%. It's as if we've been handed the universe's birth certificate, listing its fundamental components in black and white. These percentages aren't just abstract figures, they're encoded in the CMB's subtle temperature fluctuations. Picture the early universe as a simmering pot of soup, with dark matter acting as the thickening agent, clumping together under gravity while ordinary matter rides its gravitational waves. Dark energy, still dormant at this stage, would later emerge as the steam pushing the pot's lid outward. Planck's measurements of these ripples, variations as tiny as 1 part in 100,000, allowed scientists to calculate the exact density of each component. The patterns match so precisely with dark matter's predicted behavior that it's like finding a fingerprint at a crime scene, confirming a suspect's presence beyond doubt. But here's what makes the CMB truly revolutionary. It's a time capsule from an era before dark energy's reign began. Back then, dark matter's gravitational pull was shaping the universe's structure, while dark energy's repulsive force was negligible. By comparing these ancient snapshots with modern observations of supernova and galaxy distributions, cosmologists can trace how dark energy's influence grew over billions of years. It's the equivalent of watching a time lapse of a seedling growing into a tree, except the tree is spacetime itself, and the unseen forces controlling its growth are only now coming into focus. The CMB also holds clues to dark matter's nature. Those tiny temperature variations, their angular size, how big they appear on the sky, depends on how dark matter interacts with gravity. Planck's data fits cold dark matter models perfectly, ruling out some alternative theories. Yet the CMB's fingerprints also raise new questions. Why do the largest scale fluctuations appear slightly weaker than predicted? Could this hint at unknown dark matter properties, or even a primordial interaction between dark matter and dark energy? The more we stare at this cosmic fingerprint, the more subtle details emerge, whispering secrets we're only beginning to decipher. What's astounding is how much we've learned from what's essentially the static on an old TV, the afterglow of creation, faded to near silence over 13.8 billion years. Planck's map is more than data. It's a Rosetta Stone for the universe's hidden language, And as we keep refining our measurements, each new layer of precision peels back another veil, bringing us closer to answering the ultimate question: what exactly is the cosmos made of? The CMB tells us the recipe, but the ingredients themselves remain as mysterious as ever. If you could see dark matter with the naked eye, the universe would look completely unrecognizable, not sprinkled with galaxies, but filled with swirling, ghostly halos of invisible mass. The latest illustrious TNG simulations, some of the most sophisticated computer models ever created, reveal this hidden architecture in breathtaking detail. These digital universes show dark matter forming vast, nested structures with dense cores and wispy outer edges, like cosmic jellyfish floating through the void. Every galaxy we see is just the tip of the iceberg, anchored in the gravitational well of one of these shadowy halos. The simulations trace dark matter's behavior from the early universe to today, showing how tiny quantum fluctuations after the Big Bang grew into an intricate cosmic web. Gravity amplified these minute differences over billions of years, pulling dark matter into clumps that range from city-sized to larger than galaxy clusters. The most massive halos act like gravitational hubs, where filaments of dark matter intersect and galaxies congregate like commuters at a train station. Smaller halos orbit these central masses like satellites, often stripped of their gas and stars by tidal forces, leaving behind nearly pure dark matter ghosts. What's fascinating is how these halos sculpt the visible universe. Their gravitational wells determine where gas pools and stars ignite, shaping the distribution of galaxies in ways that match our telescopic surveys with uncanny precision. The Milky Way's halo, for instance, isn't a smooth cloud but a dynamic, lumpy structure with subhalos, remnants of smaller galaxies it's absorbed over time. Some of these dark matter clumps might still host faint dwarf galaxies, while others are completely dark, detectable only by their subtle gravitational tugs on passing stars. The illustrious TNG models also reveal a startling hierarchy: halos within halos, like Russian nesting dolls. A massive galaxy cluster's main halo contains thousands of smaller ones, each potentially hosting its own galaxy or star cluster. This fractal structure explains why the universe looks similar at vastly different scales, from tiny dwarf galaxies to the largest superclusters. Dark matter's influence follows the same rules. Yet the simulations raise new questions too. Why do some halos fail to form galaxies at all? How do supermassive black holes at galactic centers interact with their dark matter cocoons? The answers might rewrite our understanding of how galaxies are born and evolve. One thing's certain: dark matter isn't just a passive scaffold. It's an active participant in the cosmic dance, shaping everything from the tiniest star clusters to the grandest filaments of the universe. NGC 1052 DF2 isn't just another galaxy, it's a cosmic heretic, defying everything we thought we knew about how galaxies form. Discovered in 2018, this ghostly collection of stars appears to float through space almost entirely devoid of dark matter, the very substance we believe holds galaxies together. It's like finding a car speeding down the highway with no engine, no fuel, and no explanation for how it's moving at all. At first glance, NGC 1052 DF2 looks unremarkable, a diffuse, faint smudge in the constellation Cetus. But when astronomers measured the motions of its stars, they got a shock. The stars were moving so slowly that the galaxy simply shouldn't exist under standard dark matter theory. Without the gravitational glue of dark matter, the stars should have flown apart eons ago, like a sandcastle at high tide. Yet here it is, serene and stable, mocking our understanding of cosmic physics. The implications are staggering. If dark matter is truly absent, it means galaxies can form through some entirely different process, one we've never observed before. Imagine walking into a bakery where every loaf of bread has always required yeast, only to find one perfectly risen loaf made with no yeast at all. That's the level of paradigm shift we're talking about. Some theorists suggest NGC 1052 DF2 might be the result of a violent galactic collision, where dark matter was somehow stripped away while the stars remained, like a tree losing its roots but somehow still standing. Others propose it formed from gas ejected during a chaotic merger, leaving behind a dark matter-free anomaly. But here's where the plot thickens. Not everyone agrees this galaxy is as rebellious as it seems. A fierce debate has erupted over its distance from Earth, a critical factor in calculating its mass and, by extension, its dark matter content. Some studies argue we've underestimated the distance, which would mean the stars are actually moving faster than observed, requiring more mass and possibly dark matter to hold them together. It's like realizing the car you thought had no engine was actually much farther away, making its speed seem deceptively slow. The stakes couldn't be higher. If NGC 1052 DF2 truly lacks dark matter, it forces us to rethink how galaxies are born and survive. If the distance measurements are flawed, it's a humbling reminder of how tricky cosmic detective work can be. Either way, this galactic oddball has ignited a firestorm in astronomy, proving that even our most cherished theories must withstand the scrutiny of the universe's curveballs. And as more of these impossible galaxies are discovered, like NGC 1052 DF4, its equally puzzling neighbor, the mystery only deepens, daring us to question what we think we know about the invisible forces shaping the cosmos. Deep in the heart of our galaxy, something strange is producing a shower of gamma rays, an unexplained glow that scientists have dubbed the galactic center GVXS. Imagine a massive, invisible firework display happening right now at the Milky Way's core, emitting high-energy light with no obvious source. This mysterious signal, first spotted by NASA's Fermi Gamma Ray Space Telescope, has sparked one of the most heated debates in modern astrophysics. Could we finally be seeing dark matter annihilating itself? Here's why this matters. When two dark matter particles collide, theory suggests they could annihilate in a burst of energy, producing gamma rays as a byproduct, a faint but detectable calling card. The signal coming from our galactic center matches the energy range we'd expect from certain types of dark matter particles, like WIMP with masses around 30 to 40 times that of a proton. It's like finding gunpowder residue at a crime scene where the prime suspect is an invisible arsonist. The distribution of these gamma rays also fits predictions. They're concentrated in the galactic center, where dark matter should be densest, and fade smoothly outward, just as models suggest. But before we declare the case closed, there's a twist. The cosmic underworld is full of alternative suspects. Pulsars rapidly spinning neutron stars spew gamma rays too, and the galaxy's crowded core hosts thousands of these faint, hard-to-spot objects. Some researchers argue that unresolved pulsars could collectively mimic the signal we're attributing to dark matter. It's the astrophysical equivalent of mistaking a chorus of crickets for a single, louder creature. Others point to past outbursts from the supermassive black hole Sagittarius, a star, which might have left behind a residual glow we're only now detecting. The debate hinges on subtle details. If the gamma rays come from dark matter annihilation, they should be smoothly distributed like mist over a lake. Pulsars, on the other hand, would create a more clumpy pattern, like twinkling lights scattered across a hillside. Recent analyses using machine learning to disentangle the signal have added fuel to the fire. Some studies claim to see the telltale granularity of pulsars, while others insist the data still favors dark matter. The truth might lie somewhere in between, a mix of both mundane astrophysics and genuine dark matter signatures, layered like competing melodies in a symphony. What makes this hunt so thrilling is the sheer audacity of the claim. Detecting dark matter indirectly through its annihilation products would be like finding a murderer by analyzing the echoes of their footsteps. Future telescopes like the Cherenkov Telescope Array will scrutinize these gamma rays with unprecedented precision, searching for sharper energy spikes that could betray dark matter's fingerprint. Until then, the galactic center GVXS remains a tantalizing maybe, a cosmic whisper that could either rewrite the textbooks or fade into the noise of the universe's endless chatter. Either way, it's a reminder that the darkest corners of the cosmos might yet be hiding the brightest clues. For over 2 decades, scientists have been sweeping the cosmic haystack for dark matter particles, certain they'd find something in the mass range between 1 giga-electronvolt and 1 tera-electronvolt, what you might call the Goldilocks zone for WIMP. This energy band, comparable to weights between a proton and a small virus, seemed the most promising hunting ground. Theory after theory predicted dark matter would show up here, nestled between well-understood physics and the unknown. Yet after thousands of experiments from underground labs to space telescopes, this entire region has come up empty, not a single confirmed signal, just static. This barren stretch of data has become so notorious that physicists now call it the dark matter desert, a vast, arid expanse where hope goes to wither. The implications are profound. This drought forces us to confront 2 unsettling possibilities. Either dark matter particles are far stranger than we imagined, slipping through our detectors like ghosts through walls, or we've been wrong about their fundamental nature altogether. Some researchers now speculate that dark matter might be fuzzy, composed of ultra-light particles with masses billions of times smaller than an electron. Others propose macroscopic dark matter, clumps as heavy as a grain of sand but spread so thin they barely interact with anything. Then there's the radical notion that dark matter isn't particulate at all but a fluid-like substance permeating space, its gravity the only trace of its existence. The desert's borders tell their own story. At the lower end, below 1 giga-electronvolt, experiments like Super CDMS and DAMA hunt for whispers of light dark matter, while at higher energies beyond 1 tera-electronvolt, colliders like the Large Hadron Collider probe for monstrous particles that might have evaded detection by sheer rarity. But that middle ground, it's become a graveyard for theories. The once favored WIMP particles with masses in this range now seem less like a sure bet and more like a generational assumption that's outlived its usefulness. Yet the desert isn't just a failure, it's a refining fire. Each null result forces innovation. Detectors are now being redesigned to catch lighter, faster particles, or to sense the infinitesimal vibrations an exotic macroscopic object might cause as it drifts through Earth. Other teams are pivoting to entirely new methodologies, like quantum sensors that exploit entanglement to spot dark matter's faintest disturbances. The desert, in other words, isn't the end of the hunt. It's the beginning of a wilder, weirder chapter. What makes this drought so fascinating isn't just the absence of data, but what it reveals about science itself. The universe doesn't owe us easy answers. Every empty plot on the graph, every silent detector, is a reminder that discovery doesn't follow a script. The desert may yet bloom with some unforeseen breakthrough, or it might remain barren, pushing us toward even more radical ideas. Either way, the message is clear: dark matter isn't hiding. We've just been looking in the wrong places with the wrong tools, guided by assumptions that the cosmos has no obligation to obey. And so the search continues, not in spite of the desert, but because of it. After all, the greatest discoveries often lie just beyond the edges of our expectations, in the places we least think to look. The quantum vacuum isn't empty, it's a seething, frothing ocean of energy where particles blink in and out of existence faster than the universe can notice. According to quantum field theory, every cubic centimeter of space, no matter how empty it appears, crackles with transient particles emerging from sheer nothingness before vanishing again. This ceaseless activity should generate an enormous amount of energy, enough to make even the most powerful supernova look like a firecracker in comparison. Here's where the math gets baffling. When physicists calculate how much energy this quantum churn should contribute to dark energy, the numbers don't just disagree with observations, they explode into the realm of absurdity. The theoretical prediction overshoots reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the most spectacular mismatch between theory and experiment in the entire history of science. To grasp how ludicrous this discrepancy is, imagine calculating the weight of a snowflake and getting an answer heavier than the entire observable universe. The vacuum's predicted energy density is so catastrophically large that if it were accurate, space-time would have torn itself apart nanoseconds after the Big Bang, preventing atoms, let alone galaxies or life, from ever forming. Yet here we are, in a cosmos where dark energy's effects are subtle enough to allow 13.8 billion years of cosmic evolution. This glaring contradiction between quantum theory and cosmology is known as the vacuum catastrophe, and it represents one of the most urgent unsolved problems in physics. Why does this theoretical train go so wildly off the rails? The trouble starts with how quantum mechanics and general relativity describe empty space. Quantum field theory treats the vacuum as a frenzy of virtual particle-antiparticle pairs, electrons and positrons, quarks and antiquarks constantly forming and annihilating. Each pair borrows energy from the vacuum for an imperceptibly short time, a quirk allowed by Heisenberg's uncertainty principle. Sum up all these fleeting fluctuations across infinite space, and you get an infinite energy density, a nonsensical result that physicists fix by imposing an arbitrary cutoff point, like ignoring waves smaller than a certain size when measuring ocean energy. Even then, the leftover finite energy is unimaginably huge. Einstein's cosmological constant, which describes dark energy's uniform push, should theoretically absorb this vacuum energy. But the observed value of the constant is at least 120 orders of magnitude smaller than the quantum prediction. It's as if you tried to balance your checkbook and found your bank account should contain enough money to buy 1 million Milky Way galaxies, but your actual balance shows $50. This isn't a rounding error. It's a screaming red alert that we're missing something fundamental about how gravity and quantum physics intersect. Some theorists propose there's a mysterious cancellation mechanism at work, where positive and negative vacuum energies perfectly balance to nearly zero, leaving behind just a faint residue we call dark energy. Others suggest the multiverse theory might explain the fine-tuning. In an infinite ensemble of universes, only those with an absurdly small cosmological constant could host life. But these ideas feel like placing duct tape over a leaking dam. The vacuum catastrophe exposes a crack in the foundation of modern physics, one that might require nothing less than a revolution, a new theory that reconciles quantum mechanics with gravity to properly seal. Until then, dark energy remains not just a mystery, but a glaring signpost pointing toward the limits of our current understanding. While dark matter's gravitational fingerprints are everywhere, a stubborn faction of physicists insists we're solving the puzzle backward. Enter TVS tensor vector scalar gravity, the most sophisticated attempt yet to rewrite the rules of the cosmos without invoking invisible particles. Developed by physicist Jacob Bekenstein in 2004, this theory isn't just an update to MOND. It's a full-blown relativistic overhaul, stretching Einstein's framework to accommodate bizarre cosmic behavior without dark matter's shadowy crutch. TVS operates on a radical premise. What if gravity behaves differently when its pull becomes incredibly faint, like at the edges of galaxies, because space itself has hidden layers? The theory introduces two invisible fields alongside gravity: a scalar field that tweaks Newton's laws in low acceleration regimes, and a vector field that nudges light's path to mimic dark matter's lensing effects. Together, they're like stagehands adjusting the play's lighting and props to create illusions of unseen actors. When a star orbits a galaxy's outskirts, TVS argues, these fields amplify gravity's pull just enough to explain the motion without dark matter's extra mass. The math is elegant, but the universe is ruthless. TVS initially celebrated victories where MOND struggled, like predicting gravitational lensing patterns in some galaxy clusters. Yet cracks appeared as observations sharpened. The bullet cluster's stark separation of mass from visible matter remains a thorn in TVS's side. No tweak to gravity cleanly explains why most mass barrels ahead like phantom boxcars in a cosmic train wreck. Worse, when astronomers mapped the cosmic microwave background's subtle fluctuations, TVS couldn't replicate the precise patterns dark matter models nail effortlessly. It's like trying to rebuild a watch with half the gears missing. The hands might move, but the mechanism never quite keeps time. Other modified gravity theories have sprinted into the fray, each with unique twists. Some, like entropic gravity, propose gravity isn't fundamental but emerges from quantum entanglement, a cosmic illusion woven from information theory. Others, like superfluid dark matter, blend both approaches, suggesting dark matter isn't particulate but a bizarre quantum fluid bending spacetime from within. These ideas dazzle with creativity, but the same stubborn obstacles remain. None fully explain the diversity of galactic rotations, cluster dynamics, and primordial universe data without smuggling in hidden assumptions. The irony, these theories often end up more convoluted than the dark matter they aim to replace. TVS's equations sprawl into pages of dense tensor calculus, while WIMP glide through standard particle physics like honored guests. Yet their persistence matters. Every time a modified gravity theory fails, it sharpens our understanding of where dark matter's fingerprints must lie. And occasionally, as with TVS's prediction of unexpected stellar motions in some dwarf galaxies, they uncover anomalies that push mainstream science to ask better questions. Perhaps the universe is hinting that both sides hold shards of truth. Maybe dark matter exists, but gravity isn't quite Einstein's masterpiece in every corner of reality. Or perhaps we're witnessing a Copernican revolution in slow motion, where the real breakthrough lies not in choosing between invisible matter or tweaked gravity, but in discovering some third option that renders the debate obsolete. Until then, theories like TVS stand as daring thought experiments, reminding us that even our best models are provisional sketches of a cosmos still holding its deepest secrets close. After decades of hunting in the dark, the next generation of experiments is preparing to shine an unprecedented light on these cosmic mysteries. Leading the charge is LUX Zeppelin, the most sensitive dark matter detector ever built, lurking nearly a mile beneath the Black Hills of South Dakota. This ultra-pure liquid xenon time capsule waits in total silence, shielded from cosmic rays by a mountain's worth of rock, ready to catch the faintest whisper of a WIMP collision. Its predecessor, LUX, ruled out entire classes of particles. Now LZ's 10-ton target volume and 1,000-fold sensitivity improvement could finally spot dark matter's elusive recoil, like hearing a pin drop in a silent room after years of listening through stormy weather. Meanwhile, floating 1,000,000 miles from Earth, the Euclid Space Telescope approaches its mission with an entirely different strategy. Rather than waiting for dark matter to come to us, Euclid will map its gravitational influence across 10 billion years of cosmic history. By precisely measuring the distortion of light from millions of galaxies, an effect called weak gravitational lensing, it will reconstruct the invisible scaffolding of dark matter spanning a third of the observable universe. Think of it as cosmic tomography, scanning the universe's skeletal structure by watching how light bends around its hidden curves. Combined with galaxy redshift surveys, Euclid could reveal whether dark energy's strength has changed over time, potentially catching quintessence in the act of evolving. But perhaps the most ambitious project lies at the frigid heights of the South Pole. CMB-S4, an array of ultra-sensitive telescopes tuned to the cosmic microwave background, will examine the afterglow of the Big Bang with 50 times the resolution of Planck. Its goal, to hunt for primordial gravitational waves, ripples in spacetime from the universe's first moments that could unveil dark matter's connection to supersymmetry or extra dimensions. More remarkably, by measuring how dark matter's gravity subtly delays these ancient light waves, CMB-S4 might indirectly weigh individual dark matter particles, even if they never interact with ordinary matter. It's like deducing the shape of a shadow by studying how it bends the light passing by. These experiments represent just the vanguard. Quantum sensors now under development could detect dark matter's feeble gravitational pull directly without relying on particle collisions. Particle accelerators like the proposed Future Circular Collider might manufacture dark matter in high-energy smash-ups. Even pulsar timing arrays networks of ultra-precise cosmic clocks are joining the hunt, searching for distortions in spacetime that could betray dark matter's presence. The coming decade promises something extraordinary. We may finally transition from inferring dark matter's existence to actually characterizing its properties. Whether through direct detection, cosmic mapping, or primordial echoes, the invisible majority of our universe is running out of places to hide. And when the breakthrough comes, it won't just solve a puzzle. It will rewrite our understanding of reality's fundamental ingredients. The only question is which experiment will hear the universe's best-kept secret first. The universe isn't just mysterious, it's almost entirely made of stuff we can't see, touch, or even fully explain. This unsettling truth is captured in the Lambda CDM model, our best blueprint for how everything fits together. Picture baking a cosmic cake where the ingredients are wildly lopsided. A pinch of ordinary matter, just 5%, to account for every star, planet, and living thing we've ever observed. Then comes a heaping scoop of dark matter, 27% of the recipe, binding galaxies together with invisible gravitational hands, but the real shocker. The remaining 68% is dark energy, a force so baffling it's actively stretching the fabric of space itself. Think about that imbalance for a second. Everything humanity has ever studied, every mountain, ocean, and galaxy, is a mere rounding error in the universe's ledger. The rest, a vast, uncharted territory of shadows and unseen forces. Even more humbling, the Lambda CDM model isn't some fringe idea. It's the consensus framework backed by everything from the cosmic microwave background to the motions of distant supernova. It fits the data beautifully, yet it feels like a detective outlining a crime scene while admitting they have no idea who the culprit is or how they pulled it off. Take dark matter first. We know it's there because galaxies rotate too fast, clusters bend light too sharply, and the early universe's structure couldn't have formed without it. But after decades of hunting, we still don't know what it is. Is it a particle, a field, a cosmic illusion caused by gravity behaving differently on large scales? The Lambda CDM model stays silent on the details, treating dark matter as a placeholder for whatever's making gravity stronger than it should be. It's like labeling an ingredient in a recipe as magic flour because you know the cake needs it to rise, even though you've never seen it or know where to buy it. Then there's dark energy, the universe's most dominant and most puzzling component. Unlike dark matter, which clumps around galaxies, dark energy appears perfectly uniform, woven into the vacuum of space itself. Its repulsive gravity is why the universe's expansion keeps accelerating, but here's the kicker. We don't know why it exists or why it's so weak compared to theoretical predictions. Quantum mechanics suggests empty space should fizz with energy, but dark energy's observed strength is a factor of 10 to the 120 times smaller than calculations say it should be. That's not a small discrepancy, it's the largest mismatch between theory and observation in all of science. The Lambda CDM model shrugs and calls it a cosmological constant, Einstein's old fudge factor resurrected to paper over our ignorance. What's truly wild is how little ordinary matter matters in this grand scheme. That 5% includes every black hole, every nebula, every human brain that's ever pondered the cosmos. The elements forged in stars, carbon, oxygen, iron, are cosmic afterthoughts in a universe dominated by dark ingredients. It's as if we've spent centuries studying the foam on a cappuccino while ignoring the coffee beneath, only to realize the cup itself is expanding. Yet for all its gaps, the lambda-CDM model works astonishingly well. It predicts the cosmic microwave background's fluctuations, explains galaxy rotations, and accounts for the universe's large-scale structure. But it's also a reminder of how much we're missing. Like a brilliantly engineered machine with 2/3 of its parts labeled unknown, it hums along perfectly while hiding its deepest secrets. Maybe that's the most mind-blowing fact of all, that science's most successful model of reality is at heart a confession, a map of the cosmos with most of its territory still marked "Here be dragons." We've journeyed through the cosmic shadows, uncovering truths that defy intuition, a universe where 95% of reality is invisible, where galaxies spin faster than gravity should allow, and where empty space itself pushes the cosmos apart with inexplicable force. The sheer scale of these mysteries humbles even the sharpest minds. Dark matter's ghostly grip shaping galaxies we see, dark energy's relentless push stretching the fabric of space-time, and the haunting possibility that both might be whispers of physics beyond Einstein's wildest dreams. Consider the audacity of our position. We're stardust-built beings perched on a pale blue dot, decoding a cosmos that's actively hiding its secrets. Every clue, from the bullet cluster's gravitational sleight of hand to the vacuum catastrophe's staggering math, points to a reality far stranger than the standard model can explain. Maybe dark matter isn't a particle at all, but a shadow cast by unseen dimensions. Maybe dark energy's pull is the first hint of a quantum gravity theory waiting to be born. The answers, if they come, won't just fill textbooks, they'll rewrite them. This isn't just astronomy, it's a detective story where the universe itself is the suspect, leaving cryptic trails in bent starlight and redshifted supernova. And the most thrilling part, you're here for the breakthrough. Every new telescope, every deeper underground lab brings us closer to peeling back the veil. The next decade could reveal dark matter's identity, catch dark energy evolving, or just maybe unearth a truth so radical it shatters our understanding of reality itself. So stay curious. The cosmos has spent 13.8 billion years orchestrating this mystery, and we're just beginning to hear its tune. Hit subscribe, because the greatest chapters are still unwritten, and together, we'll chase these cosmic ghosts until the shadows give up their secrets. The universe is stranger than we imagined, and the best is yet to come.